And let me see. So before, like, so before we go to the the project section, I want to show you, kind of like show you some videos. Not sure, have you seen this kind of like a MIT mini cheetah before? Have you watched this video before?
Yeah.
Yeah, so I think this has been a very popular, maybe one of the most, yeah, right, there's some echo. Yeah, one of the most popular robot video recently. So basically, you know, for this cost project, for the cost project, we initially planned for you to make something either like this or exoskeleton, right? Something pretty, like basically you will work on a physical robot. So, but we have to convert it to this simulation-based product. However, the core part, the knowledge that you can learn through this Simulink simulation is very useful to develop robots like this. So basically, those kind of robots, they also use quasi-direct drive actuation, and also basically a lot of stuff you learn here in this course, like encoder, PMW, bandwidth, and almost everything you learn here is very essential for you to understand robotics. So basically prepare you for the next phase of your future career. And especially if you have interest in robotics or automation. So they are very useful stuff. So, you know, it's not just something something written on the textbook. It's something that you can see how useful it will be. Also, another project about exoskeleton. And so it's basically this project we are working with the National Institute of Health. So basically they are working on the exoskeleton for children with cerebral palsy. So my lab is basically working with the NIH. So we are developing lightweight exoskeleton using this quasi-direct drive actuation. You can see for this child, he can walk better by wearing the exoskeleton. But there's one drawback. Can you see one drawback from the robot? What drawback the robot has from the video?
Someone has to walk with him.
Say that again?
Someone has to walk with him as he goes.
Yeah, exactly. So that's a limitation of like many robotic system. If we want to make the robot really portable, mobile, right? So it's still very challenging, and to make the robot really lightweight. And you can imagine our goal is to make the robot really lightweight, ideally like a clothing, maybe a little bit heavier clothes, that the child can walk daily in home setting instead of walking with another person in a lab setting, right? So that's this kind of like background. So basically, the project that you do is basically will resonate those kind of like knowledge. And if you can understand those kind of simulation, and also many, also almost all the robotic projects, it starts with this kind of like simulation, either Simulink environment or MATLAB environment. Does that make sense? Okay, so let me see. I want to move to the next show video panel. Yeah, it's kind of hard for me to see you, so it's kind of weird to talk. So yeah, so basically, I want to go over the final products and clarify some questions and basically assignments, and also we kind of like revise the slides and also the coding, and essentially we offer you I think almost all the code you need, and you just need to go over it and write the report and understand that. So should be much easier with the code we just uploaded today. So yeah, so let's maybe I think before I go over the lectures. Is there something that you wanted me to clarify before I go dive into the details? Anything about the question about the final products?
I have one.
Yeah.
Would you also give us the values for the proportional, the integral, and the derivative for the PID? Or do we have to pick
I
those
think
values?
we put some value there, but I think I would rather you kind of like play with this, you know, because that's we already give the code and all the almost everything, right? So I would rather you kind of like play with the controller, and we also both in this course we covered the PID control, right? And also in 411. I think, you know, it's a really good opportunity, right? Ideally, we don't want to give you anything you start from scratch. But, you know, I understand it's not that easy for you to do those kind of work, right? So we give you all the code, but I think you need to kind of like tweak the parameters, right? And by doing that, you can practice and understand how to do this kind of like, you know, this kind of work.
And another question, for the saturation for the backdrivability, it still stays the same for the bandwidth?
You mean because of saturation limit, right?
Yes.
You mean because of saturation, can you repeat your question?
Because in both Simulink code for backdrivability and bandwidth, it requires saturation. I know they given saturation for the bandwidth, but does that limit is the same for backdrivability?
Yeah, I think it's okay. So in reality, there's always some kind of like a saturation limit, right? But in this case, I think it's all right. You don't need to worry about that. I think doesn't affect your simulation result. So basically, the reason we put there is basically we want you to realize that in real world, there's this kind of like saturation stuff, right? So, but in the code, I don't think that will affect your final results.
All right, thank you.
Yeah. Anything else you want me to clarify before I? Yeah.
Professor. Yeah, I had a question about the project tasks, basically, where it says in the first hip exoskeleton, it is saying that you should draw the control block diagram. Now, from studying the lectures, I saw that the hip exoskeleton has, you know, the unpowered state and the fixed position theta H state. So when you're asking for the control block diagram, will it be of those two states? And will we draw it by hand, or when you say draw control block, are you saying Simulink?
Right. I think honestly, I think we already gave you the kind of the answer, right? So overall, the product assignment is generally not very hard, right? And I don't know you understand the whole overall kind of like the lecture. I think basically so I think either way is okay. However, I really I think I don't want to enforce this, but I think you should do everything. I mean, should do the block diagram in Simulink, because that's the kind of like because let's say for example, right? So you have this we have a block diagram in PowerPoint, right? And also you see this is the block diagram in Simulink, right? And either way is okay, but I really think you should do the Simulink because this is really a nice tool, right? And because it's a kind of like a graphical user interface, right? You can see each component, right? Does that make sense?
Yeah. Yeah, but my question was also that in this slide itself, it says it's unpowered, and then there's another one where it's for fixed position theta H. So which one do we draw for?
Yeah, I think essentially it doesn't really matter, right? Because
okay.
As long as you have the block diagram, it's kind of like you change the conditions, right? Either so, for example, in the backdrivability, you change this to 0, right? But this doesn't change the overall block diagram, right?
Yeah, yeah.
So it's kind of like you give different input and measure different output, right?
Yeah. Okay.
Okay.
Thank you.
Any other question? So
Professor,
yeah,
if you have for the bandwidth case, right? So do your work and, for example, let's say the bandwidth you're getting is pretty low. Obviously, the parameters that you gave us are constant, which means the only thing that can be changed is PID. Is there any relation between PID controller and bandwidth such that you can tune the parameters of PID?
Right. Good question. So
to get bandwidth, to increase the bandwidth.
So let me rephrase your question. So I think your question is like how the PID controller will affect the bandwidth.
Right.
Yeah. So let's do this, right? So I think let's see how so basically I think that's actually a good question. So in this case, the short answer is PID parameters will affect the bandwidth, right? And let's think about this. If you give infinite gain, right? So the controller, if we, I'm not sure if we let's see go to a body diagram. Let's see use this body diagram as an example, right? So if we give infinite gain, and so first the PID controller will affect the parameter, right? And I think we probably didn't give you the PID parameter. I think as I said initially, it's interesting for you to tune the parameter and see how it will respond.
Okay.
Yeah.
So you're saying that definitely is going to affect the value of our bandwidth and the position that it's going to be.
Right.
Okay.
Yeah. So for example, you can see from this, I think maybe I can go over the details in the lecture. So I remember your question. So I will talk about more in the lecture. So I will talk about maybe 20, 30 minutes, go over the slides together. So I think to emphasize your question. Yeah. Any other question?
I have a question about the video. So what exactly, is it just a presentation and we're recording ourselves?
Yeah, I also talk about that. Yeah, so that's the goal we want to go over through this lecture. Yeah, I think let's start over. So you can see my screen, right? The slides, right? This let me switch to the it's a little bit slow. It's kind of weird. So okay, it goes to another screen. Give me 1 second. Let me see. Yeah. Okay. Let me see. Yeah, it's go to another projector. So I'm trying to see if I can manage to do this here. No. Maybe let me share this again. So yeah, it's not. Yeah, we will post the midterm answer. Yeah, it's a little bit tricky for the answer. Maybe I will post for a few days. Then, but yeah, okay, I will post that. Yeah, and see if we can see this. So yeah, I think this is let me see if yeah. Okay, yeah, this is a little bit annoying. It doesn't support this. Sorry, let me redo this. Yeah, maybe let me see if I can just maybe if I just do this way, it's okay. But it's not. It lost the animation. So yeah, maybe okay. Yeah. Very annoying. This is Zoom sharing stuff. Okay. I don't do this extended projection. So typically, as a student, the student in this course, they will publish some paper we already published like more than 12 papers in the last few years. So for this year, it's a little bit, unfortunately, this class, you cannot do this because we cannot work on a physical robot. So hopefully in the future, we can do. Yeah, let me share screen again. So I think this time it should work now. Yeah, wow. Yeah, it's kind of yeah, do you see the green now? This time is okay, right? So yeah, so yeah, let me know if there's some problem, like if you cannot see that, right? So essentially, we talk about a QDD, right? It's basically MAT cheetah, and also many other groups are trying to use this approach. And basically, my lab is basically pioneering this work even better than the motor MIT is using. So this is why I think we really want to, we are really excited to share this work with you. I think by doing this project, I think everyone is essentially learning the most advanced knowledge. And I also shared a PDF file, basically paper we recently got accepted. So I think as most of you are undergrad students, I think if you can learn this, I think that's really, really a lot of knowledge in robotics and control. And it really put you in a really kind of like a great position to some other students who didn't really know this work. So basically, we talk about, in this slide, we talk about a series elastic actuator. And so basically you see a spring here, right? And it seemed like to be very simple structure. And, but the point I want to make actually, this kind of like QDD is not only have better mechanical performance, like those kind of performance, but also better performance. I mean, also much simpler. So let's look at one example of a quasi-direct drive actuator here, right? So this is like a hip exoskeleton developed at North Carolina State University. So one student, maybe please mute yourself so you have some noise. So yeah, so basically you can see the overall system is very complicated, right? And if we take a anatomy and see the structure of the SEA actuator, right? And you see the overall system is pretty thick, about like about 10 centimeter thickness, right? It's pretty bulky. And if you look at the internal structure, and you know, from the last slide, you only see a spring here, right? So the spring, so basically implemented as rotary spring in this way, right? Seems very simple, right? But the reality is they need this kind of like a different kind of like a shaft, right? They need a lot of components, like a harmonic gearbox. So this generates, let's say 300:1 gear ratio. And also they need some kind of like a torque sensor, some kind of like a bushing, and shaft. So it's really a lot of components. So it's very bulky and also very heavy, right? So that's the problem with SEA. It's not only the performance limitation, but in terms of practicality, it's also very, very not practical, very impractical. So put it that way, right? So I just want to double check. Can you see this slide? This is my notes.
Yes.
Okay, cool. Stop me any moment if you have a question. So basically, I think we went over
series elastic actuators, or SEAs, are actuators.
So I think we probably don't need to go over that again, but essentially, basically putting a spring, that's the elastic component, right? But in terms of implementation, it's much more complicated than that, right? So, yeah. So, yeah. Oh. Okay. So let's go to the next slide. So basically, if you go to like a today, in my website, I also give a lecture about a Quasi-Direct drive in one conference about 2 years ago. So basically, I talk about the pros and the cons of different actuation method. And essentially, the point we want to make is with the Quasi-Direct drive, we can make the robot behave more like a human. Because for human talk, for human joint, we require high torque and the motion of human. And for the speed, and the motor can generate much higher speed than human requires. So that I think we talk about this. So basically, we call this the biomimetic actuator. So it's high torque and a lower speed. So more or less like a human actuation. Yeah. So this kind of like so very different with the conventional actuator. So basically, we want it to be behave look like this, but the conventional actuator, they have opposite property. So if we can obtain those kind of feature, and we can have this kind of like a nice fluid motion, like a human, the robot, it can generate this kind of like a fluid human behavior. And from this, let me see. So I think yesterday I emailed you what's the bandwidth. So basically, it quantifies the kind of like the response speed, how fast it can respond to a changing reference input command. So typically, the input is we give an input is a kind of like a sine signal, and this let's say sine theta, and if this is our force, right? And we want the robot to track this like a signal, right? And we can either give a sine signal or chirp signal. So for example, the simple case is a sine signal, and we can increase the like omega t, for example, sine omega t. We can increase the speed, I mean the frequency and omega, and observe the response, right? So in this case, we want to see in the control system, bandwidth is defined as the frequency at which the output. So basically, we use the output, you know, in terms of transfer function divided by the input. Output will be divided by the input, right? So when this is smaller, then basically it's -3 decibel is defined as like bandwidth. So I think this is about like 70% reduction of the magnitude, right? So if I give this reference talk, right, and I want to see after this robot, how well it can track this. Let's see if this is a robot, right? So we give the robot a command, and we ask the robot to track this talk, and to see how much either the torque or force. Ideally, it should exactly track this force, right, trajectory. But in reality, as we mentioned several times before, after some like bandwidth, some omega, it probably can only do like 70%, right? The new signal. Let's say if this is 100, right, 100%, and this can only maybe track up to 30%. So by that, we define this kind of like the bandwidth of the, approximately 70% of its maximum, right? So it's only 70%, right? So that's why this number is corresponding to -3 decibel. So that's how we define this. So essentially, we want to see this magnitude, input magnitude is here. The output magnitude is here, right? We use the output divided by the input. Is that clear now? What's the definition of bandwidth? Any question? So yeah, so in terms of backdrivability, and basically, as you can see from this video, and how easy you can move this robot, right? In this case, it's very easy to move it, right? We call this very highly backdrivable, high backdrivability or low resistance, something like that, right? So we generally, we prefer this kind of movement. Backdrivability means the human, right? Human can back drive the robot, right? So the human can drive this robotic movement. And typically, there are several scenarios. So typically, we use unpowered scenario, unpowered condition. So the motor is unpowered. So in this case, we don't have any active control. So because it's unpowered and it's just the essential mechanical performance of this actuator, we want to know how backdrivable the system is. And you can imagine if we power the system, provide some like active control, yeah, we can make the backdrivability better. However, the unpowered condition characterize the underlying property of the mechanical system, right? So that's why we typically use the unpowered condition, right? So this is a very nice kind of like a golden standard condition to characterize backdrivability. And the video I sent you yesterday, you can sort of watch this again. And
I'd like to talk a little bit about system.
He talked about the definition of bandwidth, and I think he also talked about other, like for example, tracking. So it's really nice for you to understand. So we spent a lot of time to find this kind of very intuitive lecture. So try to spend some time to watch this, especially to understand what's bandwidth. And in this case, for example, we can show that like the 8:1 gear ratio, right? It's pretty easy to move it. But for 36:1, and you see it's less backdrivable, so it has more resistance, right? So that's because the gear ratio is higher. So we generally don't like this, and we like lower gear ratio. But and I said engineering is the what? Is a trade-off, right? Engineering is about trade-off. In terms of backdrivability, yes, 8:1 is better. But what's the problem with 8:1 gear ratio transmission?
RPM is lower. When you
no, so not really, right? So in terms of speed, like input, like the speed from the motor after the gear, we get the output, right? And the gear actually gear reduces the speed, right? Amplifies. So through the gear, right? Let's see, we go after the gear, the speed is basically divided by the gear ratio, right? And but the torque is amplified by gear ratio, right? So this is the output side. It was a nominal the input speed and the input torque is this way, right? So that's why the energy is constant, right? I mean, ideally, right? But the speed has been reduced, but the torque is amplified. So basically, that's why we need the gear in a robotic system. But what's the problem? So yes, we certainly want it to be smaller gear ratio because it's more fluid, right? In this case, right? But what's the limitation of the small gear ratio?
Is it less torque?
Yeah, less torque, right? So as I mentioned, like even our motor has higher torque than conventional motor, but it's still limited by the torque capability. For our motor, it can generate a 2 Newton meter. But as I mentioned, about a human ankle, it needs like a 120 Newton meter, right? So typically we need a 60:1 gear ratio, right? The reason we can use a smaller gear ratio is because we don't need to generate 100% of human biological torque, right? We can generate, let's say, 30% to 40%, right? Especially for people like the children I showed you before. They can still walk. We don't need to replace all the joint moment from the person, right? From the child, right? And but however, even we just need like, let's say, 20 Newton meter, right? We still need like about like a 10:1, this kind of gear ratio if the motor is only 2 Newton meter, right? So we still need a kind of like some kind of like a gear to amplify this. That's why it's called a quasi-direct drive, because we still use the gear, and if it's no gear, it will be considered like a direct drive, right? So that's the definition of quasi-direct drive. Yeah. So if you check about the compliance, right? So basically the backdrivability, and we use backdrive torque. So this number, smaller the better, right? Smaller the better. And you can see SEA, this black line, obviously is better than other scenarios. So that's so basically, you know, in terms of final presentation and homework, final presentation and the final report, this is essentially the result we want you to show, right? So show this result and show the backdrivability plot. Yeah, we only require you to do the SEA and the QDD, right? Only two is okay, right? So yeah. Okay. So another aspect we want to compare is bandwidth. And again, you see this vertical axis is bandwidth, right? The last one is basically about the backdrive torque, right? So basically, essentially, for the final report and the final presentation, we want you to show those kind of stuff, right? Those are two of the most important slides, plots we want to see. And the control bandwidth, in general, larger the better. And, for conventional actuation, is here, right? This is pretty good, right? 20 hertz. For human movement, 20 hertz is fast enough than most human movement, right? For human movement, maybe like a 5 hertz, right? And SEA maybe a little bit too slow, right? Think about it if you do running or some falling activity, right? And the QDD certainly is still a winner, right? And has much better bandwidth. So that's why we call it the versatile, because it has better bandwidth and also better backdrivability, right? So that's why it's we call this here, right? It's a versatile actuation, right? So yeah, so this is the paper we sent you, IEEE and ASME transaction on mechatronics. It's just get accepted, weeks ago. So as I said before, I want you to understand the most cutting edge technology in robotics, right? So yeah, this
Professor, can you go back to the Boyne's chart, the graph? I want to ask something.
Yeah, please.
So when I run my simulations for the Simulink, it starts from 0 and then it goes down and then it goes back up and then down and then it has a lot of noise. Is that okay? I know it has to do, most likely I still have to play around with the PID control.
Some noise from this bandwidth plot.
After let's say after like the 65 hertz, there's a lot of noise.
Okay, yeah. So you see that that's kind of like normal. I think you can play with the PID control, and also I think in reality for some like this kind of like when this close, so it's kind of like a resonance frequency. So it's kind of like if you don't tune this very well, you can get a very noisy plot, right? So yeah, I will show you that in the next few slides. You see something like that. So it's not smooth even in your simulation, right? So we talk about this kind of like time domain, right? So we have this time domain like analysis, right? We talk about this time domain, and I think we also this can be converted to a frequency domain. I have one question. Why do we want to convert to a frequency domain? Why not we deal with time domain?
Because calculus becomes arithmetic in the frequency domain.
So basically in the frequency domain, it's kind of like a linear, linear equation, right? So it's kind of like you can do multiply or division, right? So it's kind of simple operation. But in this case, you need to deal with ODE, ordinary differential equation, right? It's nasty to deal with in this way, right? In this way, you can use a linear, kind of very simple linear algebra operation, right? You can do plus, right? Minus, multiply, right? You can do this s multiplied by s squared. So simple, right? So that's why we want to do this with Laplacian transformation and deal with this in frequency domain. The original equation is derived in time domain, right? So that's the that's the beauty of like this kind of different domain representation, right? So if you look at a little bit of detail, right? So the input is this kind of like a voltage, and ideally, for example, in terms of frequency, bandwidth testing, we can give like a torque, right? Desired torque, right? And the torque is related to the current, and the current is related to the voltage. That's why you probably look like the voltage is the input, but essentially we are basically commanding a desired torque, right? So the torque is the actual input. And also, I think you should remember for the motor, it has an electrical component and also mechanical component, right? And the electrical component is basically those kind of like resistance and inductance, those kind of components. And the mechanical component is essentially here, right? Second order Newton's law, right? Things like here, right? So that's this kind of like a mechanical part. And then the electrical part is more on this kind of like a left portion. And I think a few lectures ago, some student asked me like why, like in this case, the transmission, basically it represents this kind of transmission, but in reality also have this damping term. So normally you probably only see this one, right? It's a K, right? And this kind of like K term. But in reality, there's also this kind of like a damping term. So that's why you also see this kind of like think about this, for example, for the series electric actuator, from this displacement, right? So this kind of like position, right? And from this, you can get the torque, right? Remember the hip exoskeleton from North Carolina State University I showed you early on, right? So basically, it's this kind of like a series electric actuator, and to kind of like to mimic this kind of like a transmission structure. And here we have this output torque, right? The torque, output torque that will be applied to the person. And in the case of the bandwidth testing, and let me show you this video. I actually emailed you yesterday about this bandwidth video from Stanford University. So basically, let's watch this together and how researchers characterize bandwidth in real life. So, maybe let's go back to this diagram briefly. You can see like in this diagram, and we want to understand the bandwidth, right? And so basically, we want to get rid of the person's influence to the system, right? We only want to look at the robot, its performance. Basically, the robot bandwidth, right? So let's look at this video together. So to do that, and you will see they actually fix the person's limb, because we don't want, so we want to isolate human motion, right? We don't want the human motion to interfere with what the machine can do, right? So basically, you see this tethered exoskeleton from Stanford University was developed at CMU, and this professor, he's walking with an ankle exoskeleton, right? And yeah, so basically, pay attention to this section. You see, we want to test the bandwidth of the ankle exoskeleton, right? They have version 1 and version 2, but they are both fixed human limb. They are fixed, right? So it looks like a little bit painful or maybe a massage type of experiment, right? So it's kind of like an interesting experiment. But the key message here, and we fix the human motion, right? And we don't want the human motion to affect the robot performance, right? Because when we talk about the bandwidth, we are talking about the robot bandwidth, right? And we want to isolate a human interference. So that's why we treat human movement as zero. Does that make sense? Yeah. So in this case, like we want to fix this human motion, and so basically we fix the theta human is 0, right? It's kind of like basically fixed to the ground, like what you see in the video, right? So the input is basically desired torque, how much torque, right? This kind of different frequency we wanted to track. Yeah, and in the second case, I mean, basically, we have this like a block diagram, and if we write up this kind of all the components, and I want to ask one question: what is this? What does this diagram? What's the physical implementation meaning of this block diagram?
The electronic circuit.
The motor circuit.
Yeah. So basically, from the relation from voltage to current, right? So this is what? This R represent what?
Resistance.
Right. So this like an inductance, right? Great. Yeah. So basically, from this we get the current I, right? And from this I to the top. Andrew, question.
I was looking at the code that you posted that's supposed to be for the solution to the project, and for one of the gains, it's BC over N. Can I share something to the screen for a moment?
I think maybe let me finish this because I understand you have a question, but you know,
okay, at the end, right?
The class first, right? So yeah, the BC is here. I just want to remind you the BC and the KC. So basically, I think the relationship from this current to torque. So basically, this is a constant, right? So this is called like a current constant. So the current from motor to the torque from the motor, right? So this is this relation. So this represents for the mechanical like a feature, right? So after this, we get a theta dot, right? So that's why you have S theta, right? And after this, this in this block diagram, what is basically the like the gear, as I mentioned, right? This gear can will reduce the speed, right? Reduce the speed and amplify the torque, right? So that's what it does here. And for this block diagram, and we can measure. So basically, we convert. So this is theta, and this theta dot divided by n here, right? So basically, this the gear amplification. In this case, the KC is basically, you can think this is basically in the series elastic actuator, and we get this kind of like some kind of like a stiffness, right? In a load cell, it's essentially some kind of like you can think about like the SEA. We use a spring at the load cell. We can measure the torque, right? So that's why you get this torque here. But as I mentioned before, because in reality you also have some like damping. That's why we also have an extra term here. So that's the torque you get in this way. Any question?
For the QDD, what would our KC be?
Yeah, for QDD, it's essentially the same block diagram. It's just different parameter. Yeah, for example, for the SEA, it's a little bit squishy. So the T is smaller, right? Smaller, right? So that's the difference. So if you go to see the different parameter setting, you can see, and I will go over that, right? So one student asked me why is the -3 dB, right? Why is -3 dB? Because I mentioned it's about a 70% reduction. I mean, your input is 100, right? After the system, you get the 70%. So that's why it's basically, it's kind of like a why, you know, it's kind of like you get 70% of the performance, right? So that's why we use that as like, okay, it's kind of like a, you know, for grading, if you get a 60% of the grade, is right, it's not too bad, right? But 70% is kind of okay, right? Something like that, right? So that's, it's kind of like your GPA, right? It's kind of like a 60, maybe yeah. So this kind of like I think there may be a little bit historical why is this 70 not a 60. I think I don't know the reason, but that's kind of like a consensus. But it's generally the -3 is corresponding to 70%. So that's why it's defined in this way.
And Professor,
yeah, go ahead.
You're going to explain the relation between the PID and the bandwidth, such that.
Yeah, I think for that one, I think please go to the PID lecture. I talked about if you have a bigger P, and basically you can get a better bandwidth, higher bandwidth. So basically, if you think about the transfer function, if you get a higher P, so basically you move this higher, right? Does that make sense?
Yes.
You move this higher because you multiply by again. Let's say if you multiply by 100, you are basically shifting the overall system, because don't forget this log relation, the vertical one, right? So it's kind of like a linear, right? Linearly, you shift it upper higher. You can see this bandwidth has to be increased, right? However, if you increase bandwidth, there's also some stability issue. Again, it's trade-off problem, right? So that's the problem. So it's you cannot infinitely increase your bandwidth, right? So that's so P and also stability, right? So because typically, if we lift it this way and you see a higher bandwidth, so typically noise has higher bandwidth for noise, right? So this will you can transfer this kind of talk, but also it's more vulnerable to like a disturbance, right? So we don't want the bandwidth to be too high. I mean, you know, so it's always a trade-off issue, right? So let's go to the next slide. So basically, we can model, right? So this red block is essentially this G here, right? And here you have the PID, right? This is your PID, right? And basically you can derive this kind of like a transfer function. We already derived this for you, right? So this kind of a relation here, right? And let's go back to this bandwidth testing, right? So basically, essentially, we want to this the input, and we want to see the output talk, right? So this is the output, right? And we fix the human motion, and for the input, we can change, let's say 1 Newton meter, and we change the different frequency, right? We want to sweep, right, from 0 hertz to let's say 10 hertz and 20 hertz. But for a chirp signal, it gives you a continuous input, so you don't need to manually tune your system, right? You don't need to tune manually from 0 in a discrete manner. That make sense? Yeah, let me start over the lecture because there's some like a update from this file. So basically, a chirp signal is kind of like continuously changing your input frequency. So that's basically a smarter way to do this frequency like a characterization, right? So yeah, let's. Anyone think this is not a you don't understand anything I mentioned? Feel free to stop me, okay? Don't be shy, and you know, my goal is to have you to understand the stuff.
Professor, could you explain the chirp function?
Yeah, so chirp function is you can yeah, okay, the short answer is Google. So basically, as I mentioned, like if without the chirp signal, let's say you want to, so basically you want to know the change different input frequency, right? Let's say you do a 1 hertz input sine signal, right? This is a sine, and also you do this is one frequency you try. Then you do like maybe 10 hertz, so much faster, right? Frequency, right? You do a 10 hertz. Then if you, okay, you know, okay, 10 hertz is okay because we know for the QDD it can reach about 60 hertz, right? So 10 is not enough. Let's do maybe 20 hertz. You know, it's manual, right? You need to manually do this kind of like a different frequency. But for the chirp one, you can just use one block diagram from a Simulink. Simulink has this chirp function, and use one function, you just define this. It will continuously sweep from low frequency to high frequency. Okay, yeah, okay. Yeah, I see what you mean, okay. Let me see, I think let me finish this quickly. I think someone asked me to go over the code directly. I will ask my student to go over the code with you step by step. And Andrew, which code you are referring to?
The bode cal function, which I think takes the outputs from the simulation and it like filters them.
Yeah, let me try to open my MATLAB. So
the code also had functions like fast Fourier transform. If you could explain the significance of that as well, that'd be great.
Okay. I think yeah. I asked my student to check. I think she probably only checked the Simulink, but not the. Yeah, let's see if I can open with the computer is kind of slow. Open with span. Which part is you see? Oh, FFT. Okay. Okay. No. Okay. Yeah, let's see if I can see this. Yeah, it's kind of FTD. Yeah, let me open. So, but first, you know why people do Fourier transformation? You know why?
To change things from the time domain to the frequency domain?
So for example, if you have a frequency, right? Like let's say if you hear some like a music, there are some music has higher pitch, some music has a lower pitch, right? So that's makes the difference, right? So in that case, we want to know the frequency, right? And if it's a higher pitch, basically it's a higher frequency. Pitch is basically the frequency, right? And so basically a Fourier transformation tell you the dominant frequency of the signal. Yeah, so let me see this. You don't have to you can comment this out. I think it's just, you know, we just want to know. So basically, let's see this TD. So you see this actually TD I think is a desired talk, and the TA is you can see my screen, right?
It's blurry right now.
Blurry. Okay, let me copy this code to this. Can you see my screen?
Yes. Also, it appears that in the code that you posted, they only use the bode cal for the bandwidth analysis, and I don't believe they use it for the backdrivability analysis.
Yeah, I think you are right. Because of our bandwidth, we don't check the frequency stuff, right? So the MATLAB screen is not is that clear for the MATLAB screen?
It's readable.
Better.
Better. Okay. The short answer is you can ignore this. If you want me to explain the TD, so basically we do a Fourier transformation of the desired talk, right? So we know the dominant frequency of the signal, right? And for the TA and output, right? The talk we apply to the human, right? And we know the output, the dominant frequency. And basically, so basically, is we want to just you know, plot this transfer function. So that's what it's doing here. And I think you can ignore this, and you don't need to do this part. Yeah. Is that okay now? Yeah. So yeah, so this you don't need to check that portion. Yeah. So essentially, for Fourier transformation, we want to find the dominant frequency. That's why we had some like a Fourier transformation there. Yeah. I hope this answers your question. So let me quickly go over the remaining portion. So this let's see, we talk about the bandwidth, and so if you understand this transfer function, and so essentially this transfer function, you can represent this. In this case, we put it in the PowerPoint, right? And then you can So essentially, and now you have this transfer function. It's pretty straightforward for you to convert this to block diagram. But the trick I want to mention, right? For each block, you can convert this to Simulink, right? So basically, you build this instead of inside PowerPoint. You write this in Simulink. So that's why it gives you a Simulink. So basically, you look at this block diagram, and you see, right? It was created in Simulink, right? You have this block and this block. So all those components we talked in the last few slides can be represented in this way, right? And then you plot this frequency. Let me see some question. Yeah, I've asked my student to go over the code with you, and I can. Actually, we wrote some like a README about a step by step how to do that. So let me finish this quickly. So basically, yeah. So this is like you only need to do this magnitude margin, magnitude plot, magnitude to the plot. This part you don't need to do the phase, but you get this kind of like pretty easy, because if you just in MATLAB, you can just plot this, and you can do phase plot and magnitude plot, and you can do both, but magnitude is okay. And I think someone mentioned that the frequency response doesn't look like for the SEA is a QDD, right? The SEA frequency response is not as smooth as the not a super smooth, right? That's okay. I think the code we have the both code saved in the Dropbox folder. It has 2 folders. I will go over that with you, so don't worry. Yeah. So yeah, let's the next one. So the next portion is like backdrivability. And I mentioned that we want to do the backdrivability testing in the unpowered condition, right? And the unpowered condition, basically we get rid of this. So the system is not connected to the power supply, right? In that way. And think about the video, we use the hammer to hit the transmission, right? No matter the hammer or the person, you move back and forth and to drive this mechanical system, right? So that's why it's called backdrive. Human drives this transmission. Yeah, we saved that to the Dropbox folder. It's already saved to the folder you receive. And so basically, again, it's the same transfer function. It's just we change the condition, right? The condition, this portion, right? Like the electrical, all those components, right? The gear, right? So I talk about this is the gear, right? The 1 divided by n, and reduce the speed and amplify the torque, right? And the exoskeleton transmission, right? Either is SEA or QDD, right? Either way, right? QDD, right? And the overall block diagram doesn't change. We only change the input and output. In this case, the input is think about the human, right? In the bandwidth case, human is fixed. In this case, humans start to move. Think about it, you use your hand to move back and forth, the robot, right? The input is here. This is the sine signal, right? And the output, so the output is basically here, right? Again, we want to see the output of the mechanical system, how much torque it will generate. And so basically, the resistive torque is unpowered, but it still has some resistance, right? So we change the V to 0, right? So this is scenario, right? So basically, again, so this is done in Simulink, right? So if you want me to go over the Simulink block diagram, you see this has some like a saturation. So this is like basically this is a saturation limit. We set some saturation just to represent a real scenario. And yeah, so this is a kind of like yeah. So basically,
Professor,
yeah, go ahead.
See, after the derivative block, there's the BC divided by n. Why is that divided by n if it's divided by n already?
Yeah, I think very likely this error. Yeah, this is a mistake. Yeah, I think we already divided by n here because this is gear, right?
I think the plots in the code that, like, if we run the code that you sent us in the Dropbox, they have that BC over n in them. So I think those plots are incorrect.
Okay, I will double check this part. Yeah, this might be the error. Yeah. So yeah. So again, in this case, we change the input here, right? So this is a human motion, right? You move back and forth, and we change this to 0, right? So this is everything is done in Simulink scenario. This is the top, right? The output top, right? Output top. So in this way, yeah, and you get this kind of like a plot. And from that, so basically from this terminal, and you get this plot, and you see. So essentially, you will see that. Hopefully, you get this kind of SEA has a higher resistance, and the QDD has a lower resistive top, right? So this kind of like difference, yeah. And in terms of assignment, what you will submit, yeah. So yeah, so basically, we have 2 deadlines. The first is May 13th. The second is May 20th. The reason we have this is basically we want you to send us some like some presentation and some video. And basically, I want you to give you 2 opportunities. So I want to give you some feedback, like both the video and the presentation. So hopefully you can take the feedback and polish that and generate this kind of like the final presentation and the final report. So this also, you need to do this kind of like a final presentation and the final report here, right? Just have this portion, right? This portion will repeat here. And it's just, I want to give you some feedback. That's why we put it here. And make sure it's individual presentation and individual video, right? And each video should not be no more than 5 minutes. I will show you the requirement. And upload to a YouTube video, and also email us. Also, we want you to send us a link of the raw video. Just to save to Dropbox or Google. We want to see the raw video, but don't send us an attachment. We don't have that much space. And by the 20th, you should give us a report, at least 2 pages, right? And the presentation and the video, right? Finalize version. I will give you I will grade that. And also email us the code, right? The Simulink code. And for example, you can tune your PID and something you think is useful, right? And in terms of video, no more than 5 minutes, because if it's more than 5 minutes, no one will really watch that. So, there are so many videos. And we will select some really good videos and post them to our website. And, the CUNY community, some professors, can basically see some cool stuff you have been doing, right? And one way to do this, you can use Zoom, like what you see from my video, right? And you have Zoom presentation, and here is your head, right? Something look like this, right? And I'm not doing that good because I'm doing so many things right now. But generally, we want you to show your head here because we want to see which person is presenting, right? And ideally, there's actually one configuration that I think you can make this head even bigger. So I think I will send you some instructions about that. And because we don't only want to see the slide, we also want to see students, right? Human-centered robotics, right? We want to see you. And I think we want you to talk about at least 1 minute out of this 5 minutes about what you have learned, right? Because Mr. Zhang sponsored this course, we want to use this opportunity to show him what you learned in this course, right? So basically, 1 minute about what you learned, and 4 minutes about the PPT, maybe roughly in this way. You can also do 2 plus 3 something. Yeah, if it's 5 minutes and 30 seconds, that's okay. But generally, I don't want you to go over 6 minutes, right? So don't make the video too long. And you can check my video and also some examples some other students did before. I want to maybe show you one video some students did before. So you can either, so this is kind of like a short video, I think, which is really nice, right? We don't want to see a very lengthy video. So basically, they talk about
lightweight 3D printed exoskeleton.
Right? So they talk about what they did, right? And also in the end, they talk about 1 minute, yeah.
All the electromechanical components together.
Yeah, something they learned, what they learned in this course, right? So similar. So basically, give you 5 minute limit, right, to do this. And in terms of assignment, so basically, and we talk about this, right? It's primarily about the PowerPoint file and the report. Will be written documents and the video. We'll grade all like a 1, 2, 3, and 4. It's not too much work because we already give you the code, right? You just need to write some documentation, and don't just copy paste from the papers, but feel free to rephrase something you read from paper. I'm not asking you to write a paper, right? So this is not a paper. I'm not asking you to write a paper, right? I'm just asking you to write a report, right? 2-page report, and show you what you learned through this course. And you know, some of this could be figure, right? Figure 1, figure 2, right? Something like this. You know, the actual text maybe just 1.5 page, right? And also you can add some reference. A very short report, and I think it should be manageable. And yeah, and basically talk about the modeling and compared actuation, and in terms of backdrivability and bandwidth, and use the given parameter. And of course, if you can tune the parameter, you can get better performance. That's also welcome. And derive this transfer function and transfer function for the backdrivability and bandwidth, right? So you see, in this case, the output is a talk, input is a reference talk. In this case, the input is human, right? Human movement, right? So the output is also talk, right? So you see the difference. And we also give you the parameter, and I think we update this parameter, hopefully address the problems that you saw before. And in this case, I want to give me 1 second. Let me finish this slide. So basically, if we look at the transmission stiffness, you see SEA, because it had a spring there, right? The constant is smaller, right? For QDD, we don't have spring, so that's why it's bigger, right? And for damping, they have the same damping ratio. For gear ratio, obviously they have different gear ratio. And also for QDD, it has a smaller inertia, but for SEA, because the motor, it has a larger inertia. Question? What the question you have?
I have one involving the inputs. Because in the old, in the beginning when the project was introduced, they gave us a motor radius, and this one they don't. Does that matter?
I think we already fixed this. Let me see. So the radius, because you see for series electric actuator, they typically is kind of like a pancake, right? For conventional actuator, it's typically like a sausage. That's why they have different diameter. But I think we already fixed this diameter. So I don't think you need to tune that. So just keep it as it is, because this is related to the manufacturing of the motor. You don't need to tweak this parameter.
Great, thank you very much.
Sure. Any other question?
Professor.
Yeah.
Okay, you can go ahead.
Taking a look at the Simulink code for the backdrivability again, there's a gain right after the chirp function for the human angle, and I don't know
why the gain. Are you talking about the slides? Are you talking about the slides?
I'm talking about the Simulink backdrivability _ simulation .slx.
You are talking about the lecture 11 one?
Yeah, the code. The lecture 11 code.
Let me open it, yeah. give me 1 second to open it. Share screen again. This code you are talking about? This backdrivability?
Yes. So right after the chirp function, there's a gain of 0.087. Where does that 0.087 come from?
So yeah, so you see, I think we define some parameter. So I think this is something. I think this. Let me see. I think this may be because the degree to reading conversion. Maybe because of this.
But like 1 degree to 1 radian isn't that number.
Let me check. Let me check. I think this because, but it said, I mean, the point is that this doesn't really matter because the linear system, this doesn't really matter, right? So this will not affect your result because you can change so basically this backdrivability, right? And essentially, I mean, this doesn't affect your result even if it's 1 is also okay because it's just a scaling and you still get a different kind of basically we give different motion, different like a rotation, right? So this input is a human joint angle, right? And the output is tau. Doesn't really matter for this one. You can change this to 1, but I think this maybe has some physical indication, so it's better, but doesn't really matter. Let me see 1. What's the ratio between reading and degree? Let me see. Yeah, I will get back to this to you very soon. But I think
okay.
That's basically yeah.
The BC divided by N though, that's like definitely a mistake, right?
I think so. Let me double check that and yeah. Yeah, let me double check that and get back to you today. Yeah.
The purpose
okay, thank you.
Yeah, and for the simulation, I think let's see. This we wrote a README file here, right? Open your MATLAB and open this file first. Open this M file and run this M file first. SEAQDD backdrivability. So yeah, I think that's the sorry, this like run this file and so basically let's do this. Open SEAQDD. Let me see. So basically, you open this file, and basically, you see here we configure different parameter, right? So we configure different parameter, and we also, yeah, we like configure the simulation time, right? This is basically the same function. Basically, simulate this file, right? This Simulink file for 16 seconds, right? So we give this parameter. So basically, you know, you can run the Simulink from Simulink directly, or you can run in MATLAB, right? So use this command to control that. Essentially, it's the same thing, right? So this is how you how you do that, right? So wait a few seconds, then you get the backdrivability results in this way, right? Does that make sense?
Yeah, Professor.
Yeah.
How come the conventional backdrivability code is not shown here? Or do you want us to add it to the code? Because it looks like it's just SEA and QDD that you provided. I mean,
yeah, I think I try to make this simpler. So we just study study SEA and QDD, you know.
Professor, I had a question about the report. It says that you need to derive the bandwidth and the bandwidth and the backdrivability. So when you say derive, are you saying that we kind of walk through all the steps, like we start like the control block diagram, everything?
Yeah, I think in the presentation I already give you the answer generally, right? But I want you to put this down in the report and also in the PowerPoint file, right? You know, I teach you how it works. It's not equivalent to what you understand, right? So that's why I want you to go over the steps, right? And we generally already give you most of the answer, but I want you to, I mean, it's up to you, right? You can go over this step by step, or you can, I mean, you can copy and paste. But the goal is I want you to understand how it works, right?
Okay, got it. Thank you.
Yeah. So yeah, that number, as I said, right? So basically, I don't know why my student put 5 degrees. So basically, the conversion from degree to readings, right? Because we need you know, international unit like to calculate this number. This is like a power, and we cannot use the inch, degree. This is something more intuitive. Yeah, I think yeah. So in this case, that's why you got this little bit of weird number and 5 degree. And I said you can do like maybe 30 degrees. So basically, I think if we go back to the code. So, you know, honestly, I don't want to go over the code with you. I want you to, you know, you should read this. If I go over all the code, I tell you everything, right? So it's better you, if we go back to the, it's better you go over this, right? So for example, in the chirp signal, right, initial frequency is 0, target time, right? And we have this target time, and the frequency target time is TF. So basically, we define this parameter, right? TF here, right? And 1 hertz, right? But you need to tweak those parameters, and that's why, you know, we didn't tell you all the details, but we give you 99% of the stuff. So as long as you understand this, it's pretty easy for you to understand to do all stuff. Yeah.
So, Professor, for the I guess the check function, the input signal, I think it's 300 Hertz, 0 to 300 Hertz. Supposed to tune the value of the input here.
Say that again. I can't hear you very well.
To change the parameters to kind of tune the value at the input function, at the reference signal of the check function. I think it's in one of the slides, it says 0 to 300 Hertz. So are we supposed to tune that too?
I can't hear you very well. So you said some like
in one of the slides, right, that you provided, there is one of the slides says 0 to 300 Hertz. I believe the check function. Are we supposed to tune that parameter for the reference signal?
Yeah, I think you know, I don't want to answer this because you should understand how it works, right? So I already told you the transaction, you can switch this signal from low frequency to high frequency, right? And you already know that the bandwidth of the system, right? Right? You should determine what range you should try, right? You don't want to try like 1,000,000 hertz, right? Some frequency that's reasonable, right?
Right.
Yeah.
Okay. Thank you. Thanks.
Yeah. So I think I briefly went over the code with you, right? And most have been shown in the slides and also in the code here. And we put the different steps for you to do this, right? And check the README file, and they give you pretty clear instruction which file you should do first. And honestly, we should not provide this to you because it's pretty straightforward, right? And in this case, for the chirp signal, you know, ideally, you know, in this case, we should do like, you know, we should write like, let's see, because this motion, right? Chirp signal, we converted this degree, right? We assume the unit of this chirp signal is degree, right? But in reality, we need to like convert this to convert this to radian, right? So we can just do 180 divided by pi. Sorry, pi divided by 100. Depending on what the input. So I think the input, yeah. So yeah, so basically, I just want to tell you that you can have some like a parameters here, and but this doesn't really matter. You can change this to 1. That's also okay, because essentially, as long as you understand what this does, right, and as long as you understand the unit, right, either you define as the radians per second or degree per second, right, degree, right. So degree is more intuitive. That's why we convert a degree, right, to radian. Does that make sense? Yeah, you can translate. Yeah, something like this way. Right? Any other question? Two more questions. Let me see what the question are they. Yeah, you know, for the
is there a range of motion for the?
Is there a range of motion?
Like for the chirp function, like should there be a maximum and a minimum angle that we apply to it?
In terms of physical indication, yeah, you can. For example, I think. Yeah, I'm not quite sure how they define this. Yeah, that's. I think. You are talking about the magnitude or the frequency? Can you repeat your question?
No, because the chirp function, its magnitude corresponds to an angle of the human knee. If I'm understanding it correctly for the backdrivability.
Right.
And
it could be any drop. And, yeah. Go ahead.
So like I'm saying, what should we make the max and the min for that angle for the backdrivability?
I think you can put like a 30 degree back and forth, you know, for human. Let's say in this case is a hip, right? You can check hip angle or knee angle, whatever exoskeleton you want to simulate, right? It's yeah, for the hip, typically people walking, it's a positive and negative 30 degree, right? You can put in 30 degrees there. Yeah, it's okay.
Thank you.
So you can also, you know, put a larger number. Doesn't really matter, but you know, essentially you get a. As I said, it's a linear system. Yeah, it's doesn't really matter. Yeah, it's just a physical interpretation matters. Yeah. Yeah. So in this case, we convert the degree because degree is more intuitive for us to understand. But in terms of simulation, we convert degree to this kind of radius. This kind of for internal calculation. Yeah. Any other question? So this saturation limit, for example, there are like a voltage saturation, right? And also current saturation limit. So, yeah, you know, we just make this more realistic. Yeah. Any other question? So I will ask my PhD student to maybe stay online until for another 30 minutes. If you have some questions, you can still stay online so she can answer your question. And is that good?
Yes.
Yeah. I think basically you can stay longer and she can answer some questions. But I think that's all the lecture and the coding I want to go over with you today. Yeah. Okay. Okay. Yeah. Yeah. You can stay longer. Let me see if there are some other questions. So one student asked me about the drops -3 dB for the bandwidth. So I want you to understand the bandwidth is minus 3 dB is the ratio between the output magnitude and the input magnitude, right? So that's minus 3 dB. That's equivalent to 70%, right? So that's how we define bandwidth. That's the magnitude ratio. Let's see, my input magnitude is 100 Newton meter. Let's see, okay, using a simple example. For the bandwidth, the magnitude of the torque is 100. And the output, when it reaches 70, that moment is defined as a bandwidth. So the minus 3 dB is a vertical line. Don't confuse with the horizontal. The horizontal is the frequency. The vertical is the ratio between output and input. Does that make sense? Andrew, does that make sense? Yeah, I think
for the bandwidth.
Yeah, so the minus 3 dB is the input output ratio, right? So that's the vertical line, and the x-axis is a frequency.
One more question about Simulink. For the data that we take out.
Yeah.
The data that we take out when we read it, is that data still like the Laplace transform? Or when we like sim out, is that back into the time domain?
Yeah, let me see the code. Yeah, so yeah, I think this short answer is time domain.
Okay, so
yeah, let me share the screen with you. Yeah, so you mean for this number?
Mm-hmm.
Yeah, so basically, let's see. For example, here is voltage, right? Here is human input, right? They are all physical parameters, physical numbers, right? And the number you get the same out, and basically is also kind of like a time domain number, right? So it's just the block diagram is represented in frequency domain, but everything that you poke here, if you put like a scope here, you will read basically the time domain. So basically kind of like however, I think it depends on how you configure this. So for example, so yeah, the short answer is time domain, but you can also, for example, in the MATLAB, you can get the time, right? Time that the data array, right? And this is the kind of like the torque, right? And you can plot the torque against time. Does that make sense?
Okay, so I know the transfer function theory, everything is like the Laplace transform, but because it's just doing it like numerically, it still stays in the time domain.
Can you say that again?
Well, I know like for the transfer functions in theory, everything's supposed to be in the like the frequency domain,
right,
or like the S domain.
Right.
But is the way that it's able to stay in the time domain is it's just doing it all numerically and not like actual.
So I'm not sure I quite answer your, I understand your question, but maybe I can try to see. So basically, you see this block, right? Is this block? Each block is basically a S domain block diagram, right? This or this, they are S domain. But that's the beauty. You use the S domain block to, to build the relation, right? Like for example, the relation between current and voltage, right? You build this relation. The beauty is you use the linear system to frequency domain to represent the different relation. However, the benefit you get is that you can always, let's say you put a scope here, right? Put a scope here and so here and read this number anytime. And this number is a time domain number. Does this answer your question?
Okay, so because I wasn't sure if it was like the domain value or just be like the magnitude of the Laplace transform, right? Like if it took like that hypotenuse.
Can you repeat it again? You broke out. Can you repeat it again?
Okay, because I wanted to make sure it was the time domain.
Right.
Value and not like it's telling me the magnitude of like something on the complex plane.
Okay. So basically, you see this number, right? This number, right? The stop time, how long you want to do the simulation, right? You can type 100, right? Or 100 or 1,000 a second, right? So basically, in the Simulink, this gives you an array, data array. You know what I mean? It gives you a data array. It's not just like a single number. It's an array. And also from this, based on how you configure, so that's a little bit about this some. So okay, let me answer you in a simple way. So you can get a data array from each of this anywhere. You put it like a scope. If you want to get the data, you need to do this sim out, right? You can do another sim out. So this is the data, but it's represented in time domain.
Okay, thank you.
Sure, yeah. And if I can add more, so basically in the Simulink configuration, you can change, so basically it does some like a numerical calculation, which you don't really need to check. For example, you can, you can select this like fixed step or a variable step. So this is another kind of like a numerical calculation stuff. So, but for example, in this case, you can select the ODE 4, right? Range Kuta method, and then you select the fixed step, right? So this gives you like a, you know, you get the time free or time step, right? From 0, 0.0, right? 0.01, 0.002. So you get a time domain plot, and you also get this y. So you can get the time. So essentially, you get the time and you get the number you are interested in. Yeah. Any other question? So generally, I think I really think. I mean, talking to my student, I think I feel like you are very kind of like lucky because. For my students, I need to teach them like ask them to read the papers for several months. But we try to convert this kind of a little bit of advanced knowledge into this kind of simple manner. Hopefully, you can understand that. I'm not sure if any student have some question. I mean, if you think this is not intuitive, if this is too difficult, let me know. Anyone think this confusing? Feel free to let me know. Anyone think this is confusing? Is that okay? I mean, generally, I want to get your feedback overall for this project. How difficult? Is that okay or difficult or very difficult?
I can't speak for everyone, but for me, the project difficulty seems okay. And also, I learned more about mechatronics in general. I had no idea about this field before taking this course.
Who is speaking? Sorry.
Adnan, me. Yeah.
Oh, okay, cool. Yeah. Sorry that we cannot do this physical robot, and you know, this a little bit unfortunate. And but I think if you want to do some, I mean, anyone want to do some research, you are always more than welcome. And recently, I mean, today I got an email from American Society of Mechanical Engineers. So basically, the student who took my courses before got a paper accepted, and also we got some like a nomination as one of the best papers, the top 10 best papers. So we will complete for the top 3 paper in the next few weeks. I think May 19th. So I think basically want to use this opportunity to understand the core knowledge in mechatronics. I think also you can learn about Simulink, MATLAB. So essentially a lot of cool stuff, those tools, and hopefully you will find this useful in your future like a career. Yeah. Anything else? Yeah. So my student Selena, she's online right now, and she can answer some questions. So if you have no other question, you are feel free to go, and we'll post more like requirements. I think the key message for you is that I really want you to put some effort to make the presentation, and you know, when you make the presentation, the Zoom system, you can do Zoom, and so basically, I want to basically want to see your head. Kind of like a picture-in-picture scenario. I want to know who is talking. So I will select the good ones, maybe a few, about 5 people post that on our website. So you can, you know, that's also good, kind of like an award and also good memory for you. Yeah. Any questions? Anyway, I think this final product. Yeah, go ahead.
Yeah, how do we record ourselves on Zoom then?
Yeah, I think in Zoom, I think each one, because CUNY has a free Zoom to everyone, right? Each of you should have Zoom. I think if you log into Zoom, there's a section called recording, and you can just use Zoom to record it. Yeah, I think, Selena, where's the recording section?
If you log in the room and host a meeting, you are the hoster, and you have the you can record your video.
Okay. So basically, Zoom has this section. Another way is, you know, you can maybe talk maybe for 3 minutes. Then you can talk in front of the camera and merge those two together. That's also another way. So either you use Zoom, but the general idea, we want to see you, right? And we want to see each person. So that's the message here. And again, either Zoom and also PowerPoint have a recording section. And for example, let me show you one example. So you can either, for example, if you go to my website and let's go to research and go to the sensor and actuator. And I recorded this video. So this recording is completely done in PowerPoint. But you need to use camera to speak in front of the camera for another 2 minutes. So that's another thing. So you can either use Zoom or use the PowerPoint plus plus the camera to do this kind of way. Yeah, either way. Yeah. Any question? Yeah, I think Selena will stay with you for maybe for 10-20 minutes. And if you have no question, feel free to leave. And yeah, stay safe. Thank you. Bye.
Thanks, Professor.